Hey, welcome to a lesson on probability. This is the first of 3 lessons about probability, and in this lesson we'll focus on sample spaces and probability functions, which is a bit formal, but we'll try to have some fun too. Let's start with some fun review, shall we? In a moment, I'll have you pause the video. The question is, how many outcomes are possible for the experiment? These are 8 different experiments that I want you to consider. And you might solve each situation a little bit differently. And don't forget to count. All right, pause now. Okay, I trust that you did at least a few of those, but even if you didn't, stick with me for the explanations. Number 1, a single coin is tossed, so we have heads or tails. Number 2, a single 6-sided die is rolled, so we have 6 possibilities, 1 through 6. Things change a little bit for number 3. Each coin has 2 possibilities, 2 times 2 times 2. Similarly, number 4, 3 different 6-sided dice are rolled, basically at the same time. We have 6 times 6 times 6. Now, number 5. 5 different cards are drawn from a standard deck of 52. You should ask yourself, is this a permutation or a combination? And since it's dealing with cards, it's a combination. You just have to have the cards in your hand, not in order. In this case, we'll do 52C5, and that'll give you 2,500,000 and something possibilities. Number 6, we have 2 chips drawn simultaneously from a jar. So you just have 2 chips, like from a bag of chips. It could be sweet potato chips, whatever. And the concept is this. For the first chip, you have 10 possibilities. For the second chip, you have 9 possibilities because you already took a chip. Well, that's 90. But then again, this is a combination. It doesn't matter the order in which you have the chips. It matters that you have the chips. Again, some might say, okay, I want to eat this chip first and this chip second. Number 7, 5 people lined up for a photograph. What you just do is 5 times 4 times 3 times 2 times 1. And finally, 3 digits are formed from this list without repetition. What that's communicating is a permutation, and we have 3-digit numbers. So we have 3 slots. We have 5 to choose from for the first one, 4, then 3. Now 5 times 4 times 3 is 60. Let's have a little more fun. Here's the question. Which is more likely when tossing 2 dice? A sum of 3 or a sum of 5? Now, in question 2 in the previous slide, I want to point out when you roll 1 die, there are equally likely outcomes. But when you roll 2 dice, there are not equally likely outcomes. So out of the 2 here, rolling a sum of 3 or a sum of 5 between 2 dice, it's not an equal outcome. Which one is more likely? Let's consider the 2 dice. If I roll the 2 dice, I could get a 1 and a 2, or I could get a 2 and a 1, just depending on each die. Now with 5, I could roll and get a 4 and a 1, or a 1 and a 4, a 3 and a 2, or a 2 and a 3. So a sum of 5 is more likely. Probability. What is it, and how do we calculate it? Let's talk about the fun way to calculate probability first. It's simply what you want over what you've got. And we're not just talking about what you've got specifically. It's all of the possibilities and what you want out of those possibilities. As in, I roll a die, I want to get a 5, but it's possible that I could get 1 through 6. The formal way is this. And I'll define some of these terms in the next slide. If E is an event in a finite, non-empty sample space S, so sample space, we'll talk about that, of equally likely outcomes, like that die or like picking cards, then the probability of that event, like rolling a 5 or picking a king, is denoted by P of E, like a function of the quotient of the outcomes in E and the outcomes in S. The outcomes in S are the what you've got things. The outcomes in E are what you want things. Here's some probability vocab for you. You could jot these down in your probability notes there. Hopefully you have some room. Just these three terms: sample space, event, and equally likely outcomes. Sample space is simply the set of all possible outcomes of an experiment. 1, 2, 3, 4, 5, 6, that's a list, that's a set. It's the sample space for rolling a die, which we could also call the experiment. You can think of an event as not just a subset of a sample space, but an actual event. As in, you roll the die and you got the 6 that you really wanted. Aha, it was an event, yes. Or you picked a card from the deck and you got the ace that you wanted. Yes, that was a great event. Or you applied for those jobs or schools and yes, you got accepted or got hired. Now, equally likely outcomes are results that all have a fair chance, like tossing a coin and rolling a die, but not like rolling 2 dice, as we figured out in the motivation slide. And we'll talk about that a little bit more. But that's all the vocab I have for you right now. Probability distribution for the sum of 2 dice. Don't be fooled by that title. This is fun. In fact, to make this a little bit more fun, if you have 2 dice hanging around your house, go grab them and bring them back and you could play around with them. The next thing I'll have you write down is the table on the left here. Don't jot down the tree diagram over there. That's just for reference. But notice that the probabilities of outcomes start to repeat themselves. When you look at 7, that's the most probable outcome. And then 8 is the same as 6. That's how I want you to write down this table in your notes because you don't have as much space. I want you to wrap around the 8 next to the 6, 9 next to the 5, 10 next to the 4, and so on. As you write that, let me explain a little bit. To get a 2, the only method that you can use is to roll a 1 and a 1. And the probability of doing that is 1 out of 36. But why? Well, it's 6 times 6. What we've got are 36 possibilities because we have 2 dice that have 6 possibilities each. To get a 3, like we said, you could roll a 1 and a 2 or a 2 and a 1. And then 4, you could get 1 and a 3, 2 and a 2, or 3 and a 1. Notice that if you roll a 2 and a 2, you don't really know which die is a 2. You can't keep track of that, so it just counted once. And then goes down the list until we get to 7, which is the most probable possibilities. 2 for 1, 6, 2 for 2, 5, and 2 for 3, 4. 2, 4, 6 out of 36. It's possible that you don't really agree with the fact that a 2 and 2 are not distinguishable, or that for a 7, rolling a 1 and a 6 is different than a 6 and a 1, and that's okay. For the purposes of this course, you need to accept that, but you could consider your own thought process in that whole situation. Let's take a quick look at the tree diagram on the right. Notice that we could start at that point of thought that we're rolling 2 dice. So the first die, you have all 6 possibilities, 1 through 6. And then creating that second event, like a second column, is something that we'll practice a little bit later, but the second die shows you 6 possibilities that come from rolling that first die of 1, and you have those 6 listed there. And then for 2 and 3 and 4 and 5 and 6, you have all those possibilities again. So you could see all of the possibilities on the far right, that you get 2, 3, 4, 5, 6, 7, and then it starts over 3, 4, 5, 6, 7, 8. And then the only way you could get a 12 is if you roll a 6 and a 6. And that's why there's only one possibility. Let's get practical with an example, rolling the dice. Here it is. Find the probability of rolling a sum divisible by 4 on a single roll of 2 fair dice. The first question to ask ourselves is, what do we have? What have you got? What is the number of outcomes in the sample space? And those outcomes, like we just learned, is 36. Out of those 36 outcomes, what do we want? What do you really want with your dice? What is the event that we're hoping for? Well, since we need a sum of divisible by 4, we're looking for a 4, an 8, or a 12. And that's as high as we're going to get, because that's the most that 2 dice can add up to, right? Then what we'll do is add up the probabilities of each. Notice that there's a little bit more to just what you want over what you got. What we want is a 4, 8, or 12. And because the outcomes are not equally likely for rolling 2 dice, then we need to consider the probabilities of those 3 numbers. First 4, then 8, and 12. And we could get any of those, so we add up those probabilities. In other words, we're saying I want this or that or that. All 3 of them, all 3 situations are good with us. I have a quick note about and versus or when these words show up in questions. When the word and shows up in a probability question, we have to multiply probabilities. When we multiply fractions that represent probabilities, we're making that probability less likely, the fractions smaller. It's like when I'm saying I want it to be sunny and windy. It's less likely to be sunny and windy versus just sunny or just windy. The word or, when that shows up in a question, we add the probabilities. That was like the situation we just did. We're looking for a 4 or an 8 or a 12. We're okay with any of those things. When we're willing to accept more things in an or situation, then the probability of getting that thing is more likely. So just pay attention when you see those words and what that does to the probability of the event. I need to present the probability function to you. You don't really need to write this down. A probability function is a function like any other, has a name, p, and it assigns a real number to each outcome in a sample space. One fundamental truth of a probability function is that the probability of an outcome, that's an O, not a 0, is in between 0 and 1. And it could be 0 and it could be 1. Another truth is that the sum of the probabilities of all outcomes in S is 1. So when you consider all of the outcomes and you add them together, the probability of any of those happening, either this or that or that or this, is 1. It's hard to do that in real life though, because we don't always know the outcomes, but in specific things we do. The final thought is kind of weird. The probability of the empty set, nothing happening, is 0. Now I have a practical note. You could be given a probability function. In one column you have the outcomes, whatever the things that are happening, and then in another column you have the probability of those outcomes, the output. So outcomes different than output. And what we did was we actually created one of those together for rolling 2 dice. Here's a formal summary of the example that we did when we wanted to roll a 4, 8, or 12 on the dice. I don't have a spot for you to write this either, but this is the probability of an event when outcomes are not equally likely. And so here we go. In red it says if E is any event in S, S is rolling 2 dice and E is rolling a 4, 8, or 12, then the probability of rolling a 4, 8, or 12, event E, is the sum of the probabilities of all the outcomes in E. And notice that all the outcomes in E was rolling 4, 8, and a 12. So we just had to add those up. Here's a strategy for determining probabilities. Number 1 and 2 go together. Determine the sample space of all possible outcomes. The sample space, everything together, what we've got. If the sample space has equally likely outcomes, then the probability of an event is determined by counting. Well, what do we want out of what we got? Number of outcomes in E, the event divided by the number of outcomes in S. Everything. If the sample space does not have equally likely outcomes, then determine that probability function. Many times it's just given to us, especially with the dice or some other stuff that you'll do in your exercises. Check that the conditions of the probability function are met, usually they are, and then the probability of that event is determined by adding up all those probabilities, which I talked about in the previous slide. I have one final example for you. It's about determining probabilities, outcomes in E and S. Seems a little confusing at first, but I think you'll get it. Here we go. Brennan opens a box of a dozen chocolate creams and offers 3 of them to Jesse. Let's pause for a moment. A dozen chocolate creams, chocolate, and offers 3 of them. There are 12, and he's offering 3. Then things seem to get dicey. Jesse likes vanilla creams the best, but all the chocolates look alike on the outside, so we don't really know what's what. If 5 of the 12 creams are vanilla, what is the probability that all of Jesse's picks are vanilla? First, let's consider what the sample space is, what we've got, the denominator of calculating probability. Well, it tells us in the first sentence, a dozen creams and offers 3 of them. So she's choosing 3 and 12 are being offered. 12 choose 3. Now, what's the event? What do we want? The numerator of that probability calculation. If 5 of the 12 creams are vanilla, okay, 5. What's the probability that her picks are vanilla? 5, we're choosing 3. 5 choose 3. Then we could answer the actual question. What's the probability? Well, the probability is 5 choose 3, what we want, divided by 12 choose 5 over what we've got, all the possibilities. I have one final nugget of info for you, multiplication principle of probability. It simply says that if you have 2 events and you want both of them to happen, an AND situation, then you have to multiply those probabilities together. And there you have it, the fundamentals of probability. I hope you enjoyed some of that. Thanks a bunch for watching.